Hey everybody, welcome to day 6, section 9.4, graphing rational functions. So we're going to take one step further in graphing, where we graphed reciprocal functions a couple days ago, and now we are going to graph what are called rational functions. So what does that mean? Well, what is a rational function? It's a function of the form y equals f of x over g of x, where f of x and g of x are polynomials. Okay, so let's get started. Okay, all right, so steps for graphing rational functions. So we're going to talk about the steps and then kind of walk through an example at the same time. Okay, so the first thing we're going to need to be able to find are x-intercepts, y-intercept, vertical asymptotes, and horizontal asymptotes. So there's a couple more requirements for these rational functions. Okay, so let's go ahead and get started. How do we find x-intercepts? Well, think about what an x-intercept is. It's when y equals 0. So when y equals 0, we could cross multiply, and x minus 4 times 0 would just go to 0. We would be stuck with our numerator equaling 0. So to find x-intercepts, let's zoom in a little bit here. We are going to set the numerator equal to 0 and solve for x. Okay, so let's go ahead and look at our example over here. Okay, what is our numerator? Well, our numerator is x plus 2, so we set x plus 2 equals to 0, and we get x to be negative 2. So the way we're going to write it is in ordered pair. When y is negative 2, when x is negative 2, y is 0, there's our x-intercept. Okay, to find a y-intercept, so our next step is a y-intercept. Well, what's a y-intercept? A y-intercept is when x equals 0. So with a y-intercept, we are going to let x equal 0 and solve for y. Okay, you guys know what a y-intercept is. So that's nothing new. So let's go ahead and do that. All right, so to find the y-intercept in our example of y equals x plus 2 over x minus 4, we simply set x equal to 0. So 0 plus 2, plus 2 over 0 minus 4. Okay, when we simplify this, we get 2 over negative 4. Which is simply negative 1/2. So our y-intercept as an ordered pair, when x equals 0, y is equal to negative 1/2. Okay? All right, vertical asymptotes. So think about how we found the vertical asymptotes before. It was the h value, the value for which the function was undefined, and it's the value for the x value for which the function was undefined. So think about what makes a function undefined. It's when the denominator equals 0. So in order to find our vertical asymptotes, all we're going to need to do is set the denominator equal to 0 and solve for x. Okay, so in this case, our denominator is x minus 4. So we're going to set x minus 4 equal to 0 and solve for x. So adding 4, we get x to be 4. Now remember, a vertical asymptote is the equation of a vertical line. So you need to write it as x equals 4. Okay? And then finally, to find the horizontal asymptote, there's a few steps involved here. Okay, so there's different scenarios that we need to be aware of. Okay, so to find the horizontal asymptote, we have to compare the degree, the highest exponent, in the numerator to the degree, the highest exponent, in the denominator. Okay, and there's three scenarios. Scenario 1, if the degree of the numerator is less than the degree of the denominator, then the horizontal asymptote is equals 0. The leading coefficient of the numerator over the leading coefficient of the denominator. Okay, so we'll go through some examples like this and what I mean by that. Okay, and then finally the last scenario, well, we've got less than, we've got equal to. The last scenario is if the degree of the numerator is greater than the degree of the denominator, then there is no horizontal asymptote. When you get into pre-calculus and calculus, you'll get into this scenario, but for our purposes here, you really just need to focus on A and B scenarios. Okay, so let's go ahead and take a look at our example over here. Okay, so the highest degree, we have to compare the degrees of our numerator to the degree of our denominator. Okay, so if we take a look, the degree of our numerator, x plus 1, I look at the x with the highest exponent, and that's x to the first power. So in this case, the numerator, the degree of the numerator is 1. Okay, it's x to the first power. The degree of our denominator, it's the highest exponent you see on the variable. Well, it's x to the first power. That's the highest I see. So that's also a degree 1. So the degree of our denominator also equals 1. So the degrees are the same. What does it say to do? Well, if the degrees are the same, if the degrees are the same, we have scenario B. If the degree of the numerator is equal to the degree of the denominator, then we have to look at the coefficients, the leading coefficients. Okay, so let's go ahead, back up to our example here. Okay, the leading coefficient is the coefficient in front of the highest degree x. So what's the coefficient in front of this x? Well, you should recognize there is no number, so we say it's 1. Okay, so far we have y is equal to 1 over, and what is the coefficient of this x? Well, it's also 1. So our horizontal asymptote is y equals 1 over 1, and then we just simplify that and we simply say that it's y equals 1. Okay? All right. So if you have any questions on this, feel free to ask this tomorrow. Okay? But we'll get some more examples on the next page. Now let's go ahead and graph this function. Okay? The first thing we always start with are the asymptotes. So we've got a vertical asymptote at x equals 4. So let's go ahead and draw that in, make it obvious that you have an asymptote. Some of you guys forgot to graph these the other day. And then we have a horizontal asymptote at y equals 1. So let's go ahead and draw those in. Okay, now we came up with the x and y intercept, so we might as well plot those points. Okay, so if we take a look again, our x-intercept is -2, 0. Our y-intercept is 0, -1/2. So let's go ahead and include those points on our graph. So we have -2, 0, and we have 0, -1/2. So that's about there. And then just as we did the other day with our reciprocal graphs, let's go ahead and make a table of values for our rational graphs. Okay, so along with those 2 points that we came up with, if we go ahead and draw a table, x, comma, y, we're going to treat it the same way. My undefined value for x is when x equals 4. That's where my vertical asymptote is. So we can go ahead and call that undefined. All right. And we need 2 points per branch. Well, the nice thing is we already have 2 points in the branch over here. So we can include those in our table. All right. We already have -2, 0. I'll put that here. And 0, -1/2. I can always include more, okay? Then we can include 2 other points on the other side, 5 and 6. So when x is 5, we plug this in, we should get 7 for y. And when x is 6, if we plug that in correctly, we should get y to be 4. So we could plug these points in, and then we will be good to go. Okay, so 5, 7 is about there, and 6, 4. And then, of course, we can go ahead and draw our branches following along our asymptotes. So it's going to look something like that. And then this guy over here is going to look something like that. So rule of thumb, 2 points per branch. Okay, let's go ahead over to the next page and get some more practice. Okay, so now we are going to try some together, all right? And all of this information here is what we would ask you on quizzes or tests. So you need to be comfortable stating all of the required information, okay? So let's go ahead and get started, all right? Okay, so first things first, let's go ahead and, zoom in here on our first example. All right, so first thing we need to do is find the x-intercept. So remember, we set the numerator equal to 0 and we solve for x. So our numerator in this case is just x. So x equals 0. And we solve, well, there's nothing to solve here, so 0, 0. Remember what an x-intercept is when y is 0, okay? And now to find the y-intercept, we let x equal 0, and we solve for y. So y is equal to 0 over 0 minus 3, which simply goes to 0 over -3, which is simply 0. When 0 is in the numerator, that's okay. All right? So our y-intercept is 0, 0 as well. So notice those are the same. Okay? Vertical asymptotes. So the vertical asymptote, remember, we set our denominator equal to 0, and we solve for x. So x minus 3 equals 0. Solving for x, we get a vertical asymptote of x equals 3. Okay, for our horizontal asymptotes, we have to compare the degree of the numerator to the degree of the denominator. All right, so our numerator, we have an x to the first power, so it is a degree 1. The denominator, we have an x to the first power, so it's also a degree 1. When the degrees are the same, we have to look for the leading coefficient over the leading coefficient. All right, so I'm going to put LC for leading coefficient over leading coefficient. Well, the leading coefficient of this x is a 1 in our numerator, and in our denominator, we have a 1 as well. So 1 over 1, we simply get y equals 1. Okay, now if you recall from reciprocal graphs, domain went very closely with the vertical asymptote. Okay, so in this case, it's the same concept here. It's all reals except x cannot equal 3. That's our vertical asymptote. It's undefined at that point because it makes our denominator 0. Our range goes hand in hand with our horizontal asymptote. Okay, so our range can be all real numbers, but y cannot equal 1. That's where it's undefined. Okay, so let's go ahead and we can create a table of values really quickly, and then we'll go ahead and graph our function. Okay, so we have x comma y, and smack dab in the middle of my table is going to be the x value where our graph is undefined. So in this case it's 3. It goes right in the middle there. And now I need 2 points on each side. Okay, well what we notice is 0, 0. Our x and y intercepts, we can include that. We already found it. So let's use that point. Okay, so 0, 0 would be down on this side. I might choose 4 and 5 over here, and then I just need one more point on the other side of that asymptote. So I can choose 2 just because it's close to 3. And when we plug in these points, when x is 5, we should get 5 over 2, or 2.5. When x is 4, you should get 4. When x is 2, we should get negative 2. Okay, so now let's go ahead and plot our graph. Okay, so I'm going to kind of keep it zoomed in here so I can be nice and close. First thing we include are the asymptotes. So we've got a vertical asymptote at x equals 3. Make sure it's obvious. Make sure your teacher can see that asymptote. And we've got one at y equals 1. Again, make it obvious. Darken it if you need to so you can see it. Okay, and now let's just go ahead and plot those points. So we have the point 4, 4 and 5, comma 2.5, so that's about there. So this branch is going to look something like this and then follows along our asymptotes. And then we have 2, negative 2 and 0, 0. So we can go ahead and draw our branch over here, and there we have it. Okay, so if you take a look, that's what our rational graph is going to look like. Let's try one more together. Okay, so zooming in on example 2 of y equals 6 over x squared minus 4. The first thing we should notice is this x squared minus 4 should look awfully familiar to us. And we should recognize that it's a difference of 2 squares. Okay, so the first thing we're going to do is factor the denominator. Okay, so factor the denominator if we need to. All right, and so what this is going to look like is now 6 over x squared minus 4 factored is x plus 2, x minus 2. So what we notice this time is we've got 2 factors in our denominator. Okay, so let's see how this looks. All right, first thing we're going to do is we are going to find the x-intercept. So remember, we set our numerator equal to 0 because this is when y equals 0. So 0 equals our numerator of 6. Is that a true statement? Hopefully you recognize it's not. So since that's not a true statement, we don't have an x-intercept. This time there is none. No x-intercept. Okay? The y-intercept is when x equals 0. So we solve for y. So we have 6 over 0 plus 2 times 0 minus 2. All right, or we could have just plugged back into our original here, and we would get 6 over negative 4, which goes to negative 3/2. So our y-intercept is 0, negative 3/2. Okay? The vertical asymptote is when the denominator equals 0. Well, in this case, we have x plus 2 and x minus 2 equals 0. So what do you think this means? All right, this means we've got two vertical asymptotes. When x plus 2 equals 0, our function is going to be undefined. And when x minus 2 equals 0, our function is going to be undefined. So we actually have two vertical asymptotes. And solving these guys, when x plus 2 equals 0, we get a vertical asymptote of x equals negative 2. And when x minus 2 equals 0, we have a vertical asymptote of x equals positive 2. Okay, so this is a little different than what we've seen with the last two examples. All right, horizontal asymptote. Now we're going to compare the degree. We can go back to the original. I don't have any x's in the numerator, so that means our degree is 0. Okay, so the degree of the numerator is 0. The degree of our denominator, the highest power I see is a 2. So the degree of the denominator is 2. So the degree of the numerator is smaller than the degree of the denominator. Look back at the other side. What does that tell us? I'll give you a second to look. Okay, so hopefully you recognize this is the first scenario we talked about. And when the degree of the numerator is less than the degree of the denominator, our horizontal asymptote is y equals 0. Okay? Then we can quickly fill in the domain and the range because they follow the vertical and horizontal asymptotes. Our domain is going to be all reals, but x cannot equal negative 2 or positive 2. All right? And our range is all reals, but y cannot equal 0. All right? So now this time, our table of values is going to look a little bit different only because we've got two vertical asymptotes. So we're going to split up our table accordingly. Okay? So, first thing I'm going to do, let's go ahead and create the xy. And now I'm going to include both of these undefined values. So when x is 2, it's undefined, and when x is negative 2, it's undefined. And now this kind of splits up my table into the amount of branches we're going to have. Before, when we had one vertical asymptote, we only had 2 branches. This time we have 2 vertical asymptotes, so we're going to have 3 branches. Okay, so I need to choose values of x in each of these branches. So I'll choose 3 and 4 for this branch. I already have my y-intercept, and that is going to occur in this branch here. So that's 0, negative 3/2. I've already got that one covered, but I'll need another one, so maybe I choose 1. And then over here in this branch, we could choose negative 3 and negative 4. Okay, we just have to be careful when we're plugging in. When x is 4, we should get y to be 1/2. When x is 3, we should get 6/5. When x is 1, we should get negative 2. When x is negative 3, we should get 6/5. And when x is negative 4, we should get 1/2. Okay, so now if we go ahead and we graph this function, we always start with our asymptote. So we've got a vertical one at x equals positive 2 and at x equals negative 2. And we've got a horizontal at y equals 0. Again, make it obvious that you're drawing in these asymptotes. Okay? And now let's just go ahead and plot points. We're at 4, 1/2. We're at 3, 6/5, so it's just past 1. And now our branch is located in the upper right. Our middle branch, we have 1, negative 2. We have 0, -3/2, so that's about there. And I'm just going to be contained within the middle here. Our asymptotes keep us in that area. And then finally, we have the ordered pairs -3 6/5, and then -4 1/2, and we can go ahead and draw in our branch. So this one was definitely a trickier one, only because we had multiple vertical asymptotes here. What I want you to do now is try this third example on your own, and we will go over this in class tomorrow. So in order to receive credit for your notes, you better attempt this problem. Okay? Have a good night. Bye.